Okay, so in the lectures of the previous week, we have introduced the idea of quasi-static approximation, quasi-static circuit, which means that for lump circuit, for the conventional circuit theory, the fields can be represented with zeroth order fields and first order time variant field. For example, the direct product of current is magnetic field, as the Hy sub-zero shown in this plot. And if you have time variant currents, then not only the zeroth order of magnetic field, the first order of electrical field can be produced. So the two terms are the so-called quasi-static approximated field, including the static field and the first order time variant field. Of course, you can have higher order terms, but they only appears when the circuit size is in the same order of the wavelengths that we are interested. So we have shown last week the so-called quasi-static approximation, the condition for valid quasi-static approximation. That is, the size of the circuit must be much smaller than 1/6 of the wavelengths. Okay, so only when the circuit size and wavelengths are in the same order or smaller than the wavelengths will we see higher order terms. Otherwise, you only need the static terms and the zeroth order term and the first order term to get a good approximation of the general behavior of your circuit. On the other hand, as the frequency goes higher or the wavelength goes smaller than the wavelengths, if the wavelength is smaller than the circuit size, then a circuit component which is originally used as an inductor can show capacitive properties. And so is for the capacitive components. A capacitive components in the low frequency may exhibit inductive behavior at higher frequency. All right? So we will look more examples about this in today's lecture. So the next topic we would like to discuss is the electric field system and magnetic field system. Physical structure can be classified as electrical field system and magnetic field system depending on what? Depending on whether the electrical field or the magnetic field is predominant, which means for static source, for static current source or static voltage source, what kind of field resides within the structure? For example, this structure, for this particular structure, parallel plate with N connected, if you apply current source within this structure, if the current source is static, which means the amount of current is the same all the time, then you have only magnetic field within this structure. Therefore, it's referred as a magnetic field system. On the other hand, if you remove the end plate on the right hand side and apply a voltage source to the left, then what happens? Well, you mean, can I still apply a current source here? Yeah, but you have no current because the end plate is removed. So you have no current, you have nothing in this structure. On the other hand, if you remove this end plate and apply a voltage source, then this structure looks like a capacitor, parallel plate capacitor. You have static charge built up at the top and bottom plate, and you also establish an electrical field between the two plates. Because the only thing you have for this when supplying a voltage source is electrical field. You only have electrical field. So for such kind of component, it can be referred as electrical field system. So for quasi-static magnetic field system, it gives rise to a time-varying electrical field, providing that the current source is time-varying. Okay, so let's begin with this equation. You have a current source, then it accompanied with magnetic field. And if the current source is time varying, the magnetic field is time varying, and so is the magnetic flux density, then you will produce electrical field in the neighborhood of this structure. So you have ES1 term. Then, of course, the time varying electrical field should provide higher order magnetic field terms as suggested with this equation. However, because the electrical field produced in this structure is relatively small, therefore we can ignore the second order magnetic field term, which means we are in the value region of quasi-static approximation. In other words, your component size is much larger, is larger than your component size is smaller than the wavelength. Therefore, you only need the zeroth order and the first order term to find a satisfying solution for this structure. So likewise, if the structure is open circuit at z equal to 0, which means that you remove the end plates on the right hand side of the parallel plate structure, and driven it with a voltage source, then the only field present between the two plates is, in the static case, is the electrical field. So such kind of structure, as you can identify, is basically capacitor. So for capacitive structure, it can be referred as an electrical field system, which means it has only electrical field in the static case. And the production of zeroth order electrical field and the first order magnetic field can be illustrated with these equations over here. The first equation we have is the Gauss's law of electrical field. That is, the existence of electrical charge is directly linked to the divergence of electrical flux density. So, which means you can produce directly from electrical charge. You can produce electrical field directly from electric charge. If the charge density is time varying, then this term is non-zero. This term is non-zero. And it brings up the, it produces the magnetic field, the first order magnetic field term, through what? Through Ampere's Kirchhoff law. And if you continue, the time variant magnetic field shall produce second order electrical field through Faraday's law. However, for a structure much smaller than the wavelength, this term, the significance of this term is relatively small. It's so small that we can neglect the high order terms. Therefore, for this capacitive structure, we only need the zeroth order electrical field term and the first order magnetic field term. They are enough to describe the variation, field variation within structure. On the other hand, if for the same capacitive structure, if the dielectric slab between the two parallel plates is a little bit conductive, if the conductivity between the two plates of the dielectric stuff between the two plates is non-zero, then it shall produce conducting current, which makes this problem a little bit more complicated. Why? Because for such a structure, it will produce electrical field and magnetic field of the first order at the same time. So let's look at the problem geometry again. So this is the capacitive structure that I have described earlier. Without the end plate, if you apply a voltage source on the left hand side, it will build up a voltage potential between the two plates. However, if the conductivity of the dielectric slab is non-zero, then what happens? You not only build up a voltage difference between the two blades, you will also produce a current between the two plates. And of course, in most cases, the conductivity sigma is not a large number. So the current produced within these two plates is not a large number, but it's there anyway. So we must account its effect in this problem. So assuming the voltage source is a constant voltage source, so we can have the static electrical field in the medium between the plates as E equal to V sub 0 divided by T. And what you need to note is that this field, this electrical field, is static and it resides within structure homogeneously. As you can see in the equation, there's no x, y, z dependence. Okay? So the electrical field, the zeroth electrical field, is everywhere and it's the same at every position. And because the conductivity of the dielectric slab is non-zero, so you also have conducting current, JC, due to the presence of electrical field. So JC equals to sigma times E. So substitute E with V sub 0 over D. You have the conducting current across the dielectric slab as sigma V sub 0 divided by D. Its direction is in the x direction as marked with this red arrow. And as you can see, the distribution of the conducting current is uniform as well. Okay? So what happens with conducting current JC? You shall have magnetic field, right? Magnetic field is the direct product of the presence of current. The presence of electrical charge will produce electrical field directly. The presence of current will produce magnetic field directly as well. So here we have zeroth order of electrical field. And due to the presence of conducting current, you should have zeroth order magnetic field at the same time. So here is how we derive the magnetic field due to the presence of conductivity. So again, this is the Mach square equation of, this is the Amperes-Circuitial law in differential form. The curl of H equals to J, which is the direct product of sigma and E. So in this one-dimensional case, in this case, the magnetic field is in the y direction, and it can be found by taking integration with respect to the z direction. So as a result, you have minus sigma v sub 0 z divided by d plus a constant term C1. So take another look at this equation. It is the zeroth order term. Why? Because there is no dependence about omega. So it's invariant to the frequency. So this is the zeroth order term. So if you apply a static voltage across the plate, and the dielectric between the plate is not completely insulated, then you have conducting currents. Then you will have HY term. However, a very important difference between the HY term and EX term is HY term is a dependence of Z, right? EX term is not sensitive to the location. It's invariant to position Z, while the HY term is a function of Z, which means HY can be larger or a smaller number depending on the Z position. So what happens within this structure? In this structure, how do we have electrical conducting currents within this parallel capacitor structure? Because the material is not totally, is somewhat conductive, right? So you have these arrows, these black arrows, the conducting current, and so is the electrical field. And what I would like to point out is, so here is an interesting problem that you need to think of. Here is the JC current. Will they contribute to magnetic field within this structure? Will they contribute to magnetic field? This JC current going from top to bottom plate. Yeah, you think they should, but in fact they didn't contribute. Why? Because for every arrowhead going from top to bottom, using the right-hand screw, you have dot on the right-hand side, you have crosses on the left-hand side. So the magnetic field produced by these currents going from top to bottom cancel each other in most of the structure. So where does the magnetic field comes from? The magnetic field comes from the currents flowing from left to right on the bottom plate and flowing from right to left on the bottom on the top plate, left to right on the top plate, right to left on the bottom plate, which are collections of these conduction currents. Okay, so at the left-hand side, the amount of current should be larger. On the other hand, at the very right-hand side, at the very end of the right-hand side, the current approaches to zero because the plate is not connected on the right-hand side, right? So the current from top to bottom is homogeneous across the two plates, but the current density is larger on the left-hand side, smaller on the right-hand side. So again, using the right-hand rule, all the magnetic field are produced, most of the magnetic field are produced from these two currents, and their overall effect is crosses in this structure. So that's the reason why we refer them as the HY term. And as you can see here, HY term is a dependent of location. It should be larger on the left-hand side and smaller on the right-hand side. Okay? So if we want to determine the constant C1, what can we use? What kind of, where should we look to find the boundary condition? We can look at the right-hand side, because at Z equal to 0, the total currents on the top and bottom plate shall approaches 0. So the constant C1 equals to 0 because HY at Z equal to 0 shall approaches to 0 as well. So the boundary, so we can find the boundary condition. We use the boundary condition, that is the currents at the right-hand side, which is Z equal to 0, should be 0, right? So the expression for the magnetic field it can be simply expressed as this: minus sigma V sub 0 Z over D. So it's a zeroth order term because you don't see any frequency dependent in this expression. However, it's not homogeneous in this structure. It's a function of position Z. Okay? Now, so beware of this. The magnetic field is produced by currents going on the top and bottom plate. Even though you have currents going from top to bottom, the magnetic field produced by these currents are mostly cancelled. Okay? So if you apply a time variant voltage source to this structure, then both the electrical field and the magnetic field can be expressed as a time variant function, as what we have in equation 5.109. So if the voltage source is changed to V sub 0 cosine omega t, then E sub 0 equals to V sub 0 over d times cosine omega t in the x direction. The magnetic field, the corresponding magnetic field, becomes minus of sigma V sub 0 z over d times cosine omega t, and it's in the direction of the y direction. Okay, so to simplify our expression, we use the phasor notation. That is, replace the cosine omega t term with above the parameter. So E sub x0 means the zeroth order electrical field as V sub 0 over d. The cosine omega t term is not explicitly shown, but you should know that it's there. Okay? The exponential j omega t term is there. We just don't write it up. We don't write it out. So that's the zeroth order electrical field, zeroth order magnetic field. So for a time variant voltage source, what is the product of the time variant voltage source? It will produce the zeroth order electrical field will produce first order magnetic field. The zeroth order magnetic field will also produce a first order electrical field using using Ampere's Kirchhoff law and Faraday law. Okay, so the problem is you need to do the derivation of first order term twice. You need to find out both the magnetic field Hy1 and Ex1 from Ex0 and Hy0. Okay? So what is the result of the first order term due to a time variant voltage source? So let's check this out. Del Hy over del Z equals to the time derivative of Ex0. And the time derivative is represented with the j omega term. So it equals to minus j omega epsilon Ex sub 0. And it can be found by substituting the expression for Ex sub 0. So what it is? V0 over t. V0 over t. So here is the first order magnetic field term. And here is the first order electrical field term, which is expressed as minus j omega mu times Hy sub 0. So you substitute Hy sub 0 with this, sigma V sub 0 Z over d. Note that you need to integrate it, the true equation, to get the complete expression for the first order magnetic field and the first order electrical field term. So you end up with C2 and C3, two constants. So where do we look to find the C2 term? The C2 term is accompanied with Hy1, okay? And we know the boundary condition is there's no current on the right-hand side. So C2 can be determined as, easily determined as 0. Why? Because for HY term, Y1 term, we substitute Z with 0, so that at the very right end of this equations, we can see that C2 is C2 must equal to 0, so that there is no current on the very right end. On the other hand, to find out C3, you should look at which position, which location. To find out C3, you should look at the left-hand side. And what is the boundary condition on the left-hand side? The boundary condition is that we connect a voltage source, a constant voltage source on the left-hand side. So the voltage across the left-hand side is fixed. It's completely determined by the voltage source. The voltage on the left-hand side is completely determined by the voltage source. So the electrical field at the higher order term of electrical field on the left-hand side must equal to 0 at all time. So if you substitute Z with minus L at the left-hand side, it should equal to 0 at all time. So substitute this boundary condition, we can find out C3 like this. Well, it looks a little bit complicated, but it's still manageable, right? You can still find out the value, the expression for C3, even though it looks a little bit scary. Okay? So it equals to minus j omega mu times sigma v sub 0 L to the square divided by 2d. Okay, so as you can see, as we go from lower order terms to higher order terms, the expression becomes more and more complicated. So you need to understand that why we look at the left-hand side for boundary condition for the boundary condition for electrical field, and we look at the right-hand side to apply the boundary condition for magnetic field. Okay, so here is the expression for EX1 and HY1. EX1 is the first order electrical field term due to the presence of HY0. As you can see, and here is the HY1 term, which is due to the presence of EX0 terms. So why do we refer them as first order term? Because the equations, the two expressions, all exhibits the j omega term. So that's the first order time derivative term. And you can see here HY1 term is a dependence of position, which is proportional to the location Z. On the other hand, HXY1 term, which is the direct product of HY0 term. HY0 term is a dependence of Z to the first order. Here we see the dependence becomes Z to the square. Z to the square. Okay. And unfortunately, this is not the end of the first order term, because the substrate between the top and bottom plate is conductive. Therefore, the EX1 term will also produce another conducting current. which in turns will produce a first order magnetic field term. So what we need to do now, what we're gonna do now is to find out the complementary first order magnetic field term due to the presence of conductivity sigma and EX1 term. Okay, so the answers here is not complete. HY1 term is not HY1 term. This is not the complete HY1 term. HY1 term will also be produced by the EX1 term. So we will apply the J equals to sigma times E relationship to find out the supplementary first order magnetic field term. Okay, so it's a little bit complicated here, right? But once you know the physics involved, it's not that difficult. Okay, so denoting the contribution as the complementary HY1 term, which is, we know that it's produced by first order electrical field. So del H over del Z equals to minus sigma times EX1. Then we substitute EX1 with the equation we found in the previous slide like this. Then we can take integration of these terms with respect to Z. So you see it becomes more complicated. However, it's still a first order, it's only a first order omega function, right? You only have J omega term to the first order, not a second order. So it's this complementary term is still HY1 term. The constant C4 can be found to be 0. Why? Because we need to look at the right hand side. And if you substitute Z with 0 on the right hand side, the overall magnetic field should be 0 as well. Therefore, the only solution that satisfies this condition is C4 must equal to 0 because we don't have any current at the very right hand side. So after the derivation of first order magnetic field due to the presence of time variant EX0 and the presence of EX1, we have the complete expression for the HY1 term. So as you can see, they both come with the J omega term, so that they are the first order term, first order term. And this term is a dependence of Z because they are due to the presence of the EX0 term. And here, this one is more complicated. They are due to the presence of non-zero conductivity. So as you can see here, you have sigma in the second term. So the first term comes from the displacement current due to EX0, and the second term is produced by conducting current driven by EX1 term. Okay. All right. So the quasi-static approximation solution for the quasi-static field for this non-ideal structure, that is a capacitive structure with some conductivity, the complete solution can be found in equation 5.112a and b. So you have both electrical field and magnetic field. The electrical field compress zeroth order and first order term, and so does the magnetic field. The zeroth order term, the first order term, and the complementary first order term. So one interesting thing can be drawn from this result. The current drawn from the voltage source can be written as the product of magnetic field intensity times the width of the plate, which is W over here. And if you write the things up, if you substitute HY with 5.112, you end up 3 terms over here. Okay? So the zeroth order term, the two are first order term. And these things can be derived like into this one, which a little bit complicated, so you need to follow me a little bit. So, sorry. So this is the relationship between current I and voltage V, right? So if you divide I over V, you ended up with admittance. 电导嘛，电导是 admittance， 我讲 是 conductance 还是什么 ？impedance。Admittance, yeah, that should be admittance. Why admittance? And so as you can see here, this term becomes the first term, J omega epsilon WL over D. And epsilon WL over D is what? It's actually the capacitance expression for parallel capacitor, right? So our objective here is to write this thing as J omega C, okay? So keep this in mind. You can understand why we do the following for the second and the third term. So this term is moved here. It's sigma WL over D. So it's actually the conductance of the structure. You see? This is the conductance of the structure. And here, you can also have, because in these two terms, a common terms between the first and the third term is sigma WL over D, while the third terms will end up with minus J omega mu times sigma L to the square over 3, which are a little bit complicated, and we'll treat it. And this thing can be approximate, can be not that this is equal, right? From the equation at the top right corner, it's equal. But this is approximated. Under what condition? Under the condition that this is a small number, which is true which is true in general. I mean, for a capacitive structure, if the conductance of the capacitor, of the insulating layer of the capacitor is small, then this condition is satisfied. I mean, if this term is much smaller than 1, then you can use this relationship to put it into the denominator like this。好，这个回去你自己看一下好不好？用的就是这一个关系啦。那这个其实就是那个这个关系，我们还蛮常在电磁学里头用到的啊。约等于1加 nx 啊，哦，只要 x 极小于1的话，哦，好，所以事实上你是可以把这个东西换成这个啦，但前提是什么？这个东西要小，啊 ，providing that this part is much smaller than 1. Then you can rewrite the expression into this. Okay? And what is the purpose of doing so? Because we can identify that epsilon WL over D is the capacitance of the parallel capacitor. And D over sigma omega L is the inverse of the conductance, G. So it's equivalent to resistance. 应该是吧。我有点乱掉了。Okay. All right. So as you can identify from the capacitance, resistance, and the inductance, this can be identified like this: J omega C plus 1 over R plus J omega L divided by 3. And we can represent it graphically as this. The admittance of this circuit can be regarded as a capacitor in parallel with resistance R in series with an inductor L over 3. And what happens if the conductivity of this structure is totally 0? Then the resistance will become a very large number. Then this path will be disconnected. It will only show the capacitive property. If the conductance is non-zero, then it will show up as a capacitor in parallel with a conductor, with an inductor. And as you can see here, the inductance is only 1/3 of the inductance. Why? Because the inductive property is produced by the not so good conductivity within the structure. So, and because the current is not homogeneously placed, is not homogeneously existed in this structure. So the inductance of this structure is not as effective. It's only 1/3 effective for this structure. Okay? So here we can see a capacitive structure may exhibit inductive property due to the presence of small conductivity. Okay, so If there is no leaky current reside in this structure, then it will exhibit pure capacitance with this structure. Okay, so let's stop here.